All right, now it's time for discussion 1-2. We're going to talk about physical and chemical properties and changes, also techniques used to separate mixtures. All right, so first let's talk about physical and chemical properties. Physical properties are properties that can be identified without changing the chemical ID of the substance. Take that, mosquito. In other words, these are properties that you can measure just using your 5 senses. So examples include mass, volume, color, length, hardness, or malleability. There's a lot of physical properties out there, but the thing that ties them all together is we can measure them without changing what they are. If I have a sample of matter, I can measure its mass simply by putting it on a balance. I don't have to change it into a new substance. I can measure its volume by measuring its dimensions and using length times width times height, or if it's a liquid, use something like a graduated cylinder. I can observe something's color simply by looking at it. I can measure something's hardness just by tapping it, or I can see how malleable something is by smashing it with a hammer. Chemical properties are the exact opposite. They're properties that can only be identified when we change the chemical ID of the substance. In other words, we're producing a brand new substance. So these properties can be, you can also say that these properties can only be measured when the substance undergoes a chemical change. So there's many fewer chemical properties than there are physical properties, but these are some examples: flammability, toxicity, reactivity, or half-life. Flammability you can only test if you set something on fire. Now, burning something is a chemical change because it produces brand new substances. When I put logs in my fireplace and burn them, I take that wood and I turn it into ashes and smoke. Now, if I have a clear, colorless, odorless liquid, I can't tell if it's poisonous by touching, tasting, looking, or I guess hearing it. Now, reactivity just refers to how vigorously a substance undergoes a chemical reaction. We can only test that if we undergo a chemical reaction. And half-life we'll actually talk about in Unit 2, so let's leave that for now. Okay, so physical and chemical changes. Now, these definitions are very similar to physical and chemical properties, as you will see. A physical change is a change in which the sample of matter, the chemical identity of the sample of the matter remains the same during the change. In other words, when you have the change, you're going to have the same stuff at the end of the change that you had at the beginning of the change. So here this is diagrammed. Let's say I have an atom of triangle and an atom of rectangle. When I add them to each other, after the change, which is represented by the arrow, I still have an atom of triangle and an atom of rectangle. So buzzwords, things you can think of as physical changes, are all phase changes: boiling, condensing, freezing, melting. Let's think about water. Let's say you have a chunk of ice. That ice is still made up of water, so it has the chemical formula H2O. When we heat it up and melt it, it becomes liquid water, which still has the chemical formula H2O. If I heat it up more until the point where it boils, it becomes steam or water vapor, which has the chemical formula H2O. So when we go through all of these phase changes, we're not changing the chemical identity of the substance, and so they are all physical changes. Other examples would be dissolving. This one is a little bit weird, but if you think about it, when you dissolve sugar in water to make something like soda, the sugar retains all of its properties. It's still sweet. It's still tasty. You can boil away the water and you'll be left with just sugar behind. So when we dissolve things, it doesn't actually change the chemical identity of the thing we're dissolving. It just makes it become kind of part of the water, or part of the mixture, I should say. Now, bending something doesn't change its chemical identity. Stretching, cutting, etc., etc. These are all words that would represent physical changes. Now, chemical changes are the exact opposite. They are changes in which the chemical identity of the substance changes. That means that brand new substances are made. So when we diagram that, we'll still use triangle and rectangle, but here I have a molecule. We'll call that TR, because it consists of one triangle and one rectangle. Now, when we undergo this change, the molecule breaks apart into the two atoms that make it up. A molecule is considered different than the atoms that make it, and so we've created brand new substances. Let me give you a cool example of this. Table salt is sodium chloride. That means it's made up of an atom of sodium and an atom of chlorine. Actually an ion, but we'll talk about that in Unit 3. Now, sodium is a metal. Not only that, it's a metal that reacts vigorously with water. If you take a piece of sodium and throw it in water, it lights on fire and eventually explodes. So if you ate a chunk of sodium, that would make a very bad day for you. Chlorine is an element, and it is a greenish yellow gas that if you breathe will actually poison your body and basically kill you. So we've got sodium, will explode in your mouth, chlorine, which will kill you fairly painfully. But when you take those two atoms and make a compound out of them called sodium chloride, it becomes table salt, which is not only edible, but is actually necessary for life. So examples of chemical changes are burning, like I mentioned on the previous slide, rusting. When you take iron and add oxygen and water to it, you make Fe2O3, which is a compound. So we're actually creating a brand new substance called rust. Exploding, very similar to burning, and oxidizing, which we'll talk about later in the year. Okay, so we can actually classify physical properties as either being intensive or extensive. An intensive property is a property that is independent of the amount of matter present. In other words, it doesn't matter how much of the sample you have, an intensive property of that sample of matter will always remain the same no matter how much you have. That means that intensive properties can be used to identify an unknown substance because for a particular substance they will always be the same. Examples of that would be something's color. If I have a sample of copper, I love using copper as an example, I don't know why, but if I have a penny or a huge chunk of copper, they're both going to have the same color. They will also both melt at the same temperature and freeze at the same temperature and boil at the same temperature. They'll have the same density. They'll have the same specific heat and they'll smell the same. Those are all examples of intensive properties, properties that remain the same no matter how much of the sample we have. An extensive property is the opposite. They're properties that are dependent on the amount of matter present. Now, because extensive properties change as the amount of matter changes, we cannot use them to identify an unknown substance. So examples would be mass, volume, and length. As we add more of a substance, its mass will change. As we add more of a substance, its volume will also change, as will its length. Now, to illustrate why we cannot use an extensive property to identify an unknown substance, let me give you an example. I have a sample of matter. It has a mass of 2 grams. What is it? Well, you can't tell me what it is because I could have a whole bunch of things that have that mass. I have a sample of matter that has a volume of 25 milliliters. What is it? You don't know because you could have water, 25 milliliters of water, or 25 milliliters of some other liquid. All right, so let's zoom in on one specific intensive property that we talked about on the last slide called specific heat. The sciencey definition of specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now that is a very sciencey definition. The English language definition, the more simpler definition, is the amount of energy required to make stuff hot. If you have a high specific heat, that means it takes a lot of energy to change your temperature. If you have a low specific heat, it means it takes less energy to change your temperature. So think about this example. You just put a pan of water on the stove and you turn the heat on high. Now, that has only been heating for about 30 seconds or a minute, but would you want to touch the water or the aluminum pan? So take a moment, pause the video, and think about that. All right, so the pan is going to heat up faster than the water. If you touch the water after being on the stove for 30 seconds, or a minute, the water is not really going to be that hot. It might be like lukewarm. But if you touch the bottom of the pan, you're going to burn your finger. That's because the pan heats up faster than the water. Now, when you turn on the stove, when you turn on the stove, both the water and the pan are getting the same amount of, energy from the flame. So they both have absorbed the same amount of energy. Because the pan heats up a lot faster than the water, that means the pan must have a lower specific heat. Another example I like to use is sand at the beach. If there's a puddle on the beach, a tide pool, and you walk on the sand is burning your feet. So you step into the tide pool because it's much cooler. Right? So the sun came up on the tide pool and the sand at the same time, so they both received the same amount of solar energy. Because the sand has a lower specific heat, it's going to heat up a lot faster than the water. Okay, so we can actually calculate the heat absorbed or released by a substance using this formula. Q equals mc delta T. Now, a lot of kids will remember this by using the term Q equals mcat. That little triangle there is kind of like an A, so Q equals mcat. So what do all these terms mean? Q is the heat or energy, and the unit of heat we use is joules, which is capital J. M is the mass in grams of the sample. C is its specific heat, with kind of a funky unit, joules divided by grams times degrees Celsius. And delta T is a change in temperature. That that triangle is an uppercase delta. It's a Greek letter, and in science it always means change. So when we calculate the change in temperature, we're going to need two temperatures. We're going to need a final temperature and an initial temperature. To get the change in temperature, we just subtract one from the other. Now, this is a formula you need to know. In chemistry, you are not given a formula sheet. So the best way to learn it is to practice using it with the problems we give you on your homework assignments. Here's an example of a specific heat problem. It says the specific heat of water is 4.18 joules per gram degree Celsius. How many joules of heat are needed to raise the temperature of a 100-gram sample of water from 20 to 100 degrees Celsius? So when you look at these word problems, they may seem kind of confusing to you at first. But if you know the formula you need to use, the best way to tackle this problem is to label all of the data given to you in the problem. So I know that the specific heat is labeled as C. So write a little C over the specific heat. It then says how many joules of heat are needed. That term, joules, tells me that it's heat, so it's Q. And we also know that since it's asking how many joules, that's going to be our variable in the problem. 100 grams is mass, so write a little m next to it. And the two temperatures from 20 to 100 indicate a change in temperature. So we'll take the final temperature, which is 100, subtract the initial temperature to get a total change in temperature of 80 degrees Celsius. So we're going to use our formula, Q equals mc delta T. When we plug in the numbers, 100 grams of mass, a specific heat of 4.18, and a change in temperature of 80, we calculate that the change in energy was 33,400 joules. Now, whenever we do math problems in chemistry, if you write the formula, you're going to get a point. If you show your work, you're going to get a point. If you have the correct answer, you're going to get another point. So whenever you're doing math, be sure to do these three things in order to get some partial credit if you happen to get it wrong. All right, now let's talk about separating mixtures. So what type of change occurs when separating a mixture? Now I want you to actually think about this yourself and answer the question by pausing the video. So remember how mixtures and pure substances are connected together. All right, so when we're separating a mixture, we're going to separate them with a physical change. That's because the particles in the mixture are physically combined. One of the examples of mixtures I gave you in topic 1.1 was raisin bran. Now, if I want to separate the flakes from the raisins, all I need to do is pick the raisins out of the cereal. That is a physical change. Now, when we separate a compound, we have to actually undergo a chemical change because the atoms in compounds are chemically combined together. So one example of a separation technique is filtering. We use filtering to separate a heterogeneous mixture of a solid and a liquid. Now remember, we can't separate a homogeneous mixture with filtering because the particles are too small. Oh, I just answered that question below here. All right, so the particles can be separated because the particles in the heterogeneous mixture are too large to fit through the microscopic pores in the filter. Take that, mosquito. Now again, we can't separate a homogeneous mixture because the particles in the mixture are small enough to fit through the filter paper. Next is chromatography. Now chromatography is separation based on the movement speeds of different particles over a medium. Now the medium used is usually paper or wool. Now it's kind of like a race. Now because of a variety of physical properties, some pigments and inks will move across the medium at different speeds. So the faster pigments will travel further along the medium than the slower ones, and so the individual colors will get mixed, will get separated, and you'll see kind of a rainbow. Now, that's the reason we call it chromatography. Chroma is actually a prefix that refers to color. So chromatography is used for separating inks into their various colors. You can actually use YouTube to search for examples of chromatography, and you can see how that works. And finally, distillation. Distillation is separation based on different boiling points. Now, this down here is a distillation apparatus. You can see here we have a liquid in a distillation flask that's being heated. Now, this liquid is actually a homogeneous mixture of two different liquids. Now, each liquid will have its own unique boiling point. So, when we heat them up, the one with the lower boiling point is going to boil first. When it does that, the fumes are going to travel up here into this device called a condenser. Now, the condenser has water flowing in and out of it, so it's very cool. It's much cooler than the reaction flask. So when that first liquid evaporates, it's going to condense in the condenser and drip into the other beaker here where we can collect it. The liquid with the higher boiling point remains in the distillation flask, and so we've essentially separated the two liquids. So that'll be used for separating a homogeneous mixture of two or more liquids. And that is it for discussion 2-2. Please bring any questions you have to class, and thanks for watching.